Thank you. Please be seated. I had the pleasure of meeting Professor Jesse Wolfson one evening at an izakaya in Tokyo, one of those bar/eateries to which his illustrious wife and I and assorted friends would occasionally repair during our time in Japan as extremely fortunate recipients of the Fulbright Fellowship. Before that fateful evening, I had of course heard a great deal about him, and the more I've gotten to know him, the more he seems to me a precious statistical improbability. He was a mathematician, to be sure, who had nonetheless been a student of literature as an undergraduate, who, as a mathematician, was keenly interested in pedagogy, and not only in the quieter rooms and more solitary work of research, who was fascinated by and actively committed to the political life, and who, when some of my students in my freshman mathematics tutorial had questions which more than threatened to outstrip my powers to be of firmer assistance, had graciously agreed to help them talk through some questions with which they were struggling as they were writing their very first paper for that math class. This during my first year at St. John's College. And who, in literally every conversation I've had with him, astonishes me with the range of his intellect, the goodness of his character, and the capacity of his imagination. But since it is my responsibility to introduce our distinguished guest in a somewhat more traditional manner, I should also say that Professor Jesse Wolfson is an associate professor of mathematics at the University of California. At the University of California, Irvine, that his research focuses on long-standing open problems at the interface of algebra, geometry, and topology, and that his perspective on geometry emerges in part from his long-running exchange with choreographer Reggie Wilson. Delightfully, he also currently serves on the board of directors of the choreographer Wilson's Fist and Heel Performance Group, an internationally acclaimed Brooklyn-based post-African neo-hoodoo modern dance company. And as I trust you'll have gleaned from this more traditional description of Professor Wolfson's non-traditional career, he is, I think, the improbable kind of scholar from whom we are especially lucky to have the privilege of learning on a Friday night at St. John's College. Please help me welcome Professor Jesse Wolfson.
Thank you, Ron. Ron, thank you so much. It's a tough act to follow with those expectations set, so I'll try to lower them at the beginning to reset everyone. It's a great pleasure to be here to speak at the Dean's Lecture at St. John's College. I've been looking forward to this since Ron first floated the idea some time ago. The way that I understand the education here at St. John's is near and dear to my heart. I sort of almost bounced near this, and I was really excited to sort of think of how can I structure a talk that engages with the deep mathematical tradition, but brings it up in continuity to the present, to like what I and my colleagues have been really exploring in the last, today, but also in the last, 150 years. And I want to kind of do that in a way that offers repeated instances of mathematics as, on the one hand, a tool that people use to solve problems in their daily life. And some of those problems are, that sounds like hard work, can I do less of it? Maybe some math will help out, and I'll talk about some other problems. But also, it's a very imaginative activity. And so that interplay of practical need and imagination, that is a story that we'll see a bunch as we sort of trace through what the heart of modern geometry is about and how it grows out of the tradition. And I want to start with the practical. And here, I'm going to show a video. It's one of my favorites. The Muppets are running a hotel, the Furry Arms. And Ernie's at the desk here, and there's two other Muppets. And 6 penguins are staying in the hotel, and they want to order room service. And so they call down their order, and the Muppets will struggle to take the penguins' order and figure out how to relay it to the kitchen until Ernie steps in and uses one of the most fundamental tools of math available to help sort them out. So I'll show you this video, and in some sense, this is a kind of paradigm of one way of approaching mathematics. There's something you need to do, and you need some better tools for it. And then I'll sort of say some more about it after we have the videos. This will be the sort of intro.
The phone. I get it. I get it. Oh, man. Oh. Oh, hold on. It's for you, Humphrey. Here you go. Thank you. Yeah, furriers, how may I help you?
We're hungry.
Well, what would you like?
A fish.
Fish?
A fish.
Fish?
Fish.
Fish?
How about you guys?
Fish.
Fish. You got it?
Well, let me repeat that. Fish, 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 fish.
You got it.
All right, be right up with that order, Mr. Penguin, sir. Ingrid, go down the kitchen. Fish, 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 fish.
Fish, 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 fish.
No. Fish, 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 fish.
Not that easy an order, but I get it.
Excuse me, Ingrid and Humphrey, I have a better way for you to do this.
A better way? What do you mean?
Well, I just think it would be easier if you, count the fish.
Count them?
Look, I'll show you. Humphrey, you tell me the order, and I'll count with you.
Alrighty. Fish,
1,
fish,
2,
fish,
3,
fish,
4,
fish,
5,
fish.
6. See there? See what I tell you? Now you know how many fish to send up. 6 fish.
Holy mackerel! This counting thing can really save a person a lot of trouble.
Yeah. Does it work on other stuff? Say cinnamon rolls?
Yep.
Cream pies?
Sure.
Spark plugs?
Absolutely.
Wow.
He did it again.
He may be the smartest person in the whole world. All right, Ingrid, let's go get those. What are they again?
Fish.
Fish. Haha.
Oh, Chef, we need 6. Count 6 fish.
Great. So, first off, the Muppets, as sharers of mathematics, is a great cultural treasure. But we see something fundamental there, right? There's something that the Muppets need to do, and they can't figure out how to do it, or they're doing it in a way that they make mistakes. And Ernie steps in with the fundamental mathematical tool of counting and saves them some work. And this idea that from our basic to our kind of most fancy mathematical tools, at some root, are connected to practical problems that humans want to solve. And I will totally stand on understanding things as a practical problem, right? So I have an expansive notion of practice, but there are things that people want to do. Oops. There we go. And that goes back to the origin of the subject, and we'll sort of talk about this. So one of the very first uses of geometry, out of which it grows historically, is surveying, right? You could block out an area of land by physically walking around it, but that's a lot of work. And you can't do that very quickly. And so this is a papyrus from ancient Egypt, a wall painting showing surveying techniques. This is one of the first practical uses, and it turns out it's actually not just the origin of classical geometry, but it sits at the heart of the transition to modern geometry. You want to build things, and you want to build things that won't fall down after you build them. So you need to check ahead of time that you're building them in a way that they will stand for the amount of time that you want them to stand for, and that you have the amount of materials that you need to build them. You don't have to get halfway through the construction and then go find a different quarry or something like that. You want to know that ahead of time so you can be fully prepared. You want to understand how the stars move and how that connects to the seasons, right? So this is a book 10 from Ptolemy, one of the great classical uses of geometry, and an enduring use even today. And you'd like to be able to compare the amount of material that you use to build things. Or another way of saying is you want to compare areas and volumes across different shapes. Maybe when they're solids, you can't just like take your jug of water and pour it into your different container of water, but you have to, maybe it's some metal that you're using. So this is one of my favorite classical theorems of geometry. This is a page from a treatise of Archimedes called On the Sphere and the Cylinder. And this was such a big discovery that Archimedes had it engraved on his tombstone, which was rediscovered in Roman times. And the theorem is that the surface area of a sphere is equal to the surface area of the hollow cylinder of the same height. Right? So this is, again, a kind of basic instance that combines both something potentially useful but also just something that you can imagine and ask, right? And underneath this kind of enduring questions of people want to do things, people invent mathematics to solve problems, we'll see these sort of flights of imagination or explorations of imagination to ask new questions, to explore that. And so in some sense, at a deeper level in my talk, or one thing I'd like you to take away, is some inkling of how did someone become a Euclid, or a Gauss, or a Riemann, or a Thurston, these figures that transform the tradition, and how do we understand where they came from rather than just seeing these are canonical texts that were handed to us. All right, so I'm going to start with classical geometry, because it's a good place to start. Right here we have Euclid's axioms, and one thing that you see right away if you think about these axioms is that in a lot of ways they're quite practical, right? So I'll just read one of the axioms and then show a video demonstrating this. Hold on a second. Great, so the third axiom says, kai panti centro kai diastati kuklon gerfestai. We can draw a circle at any center with any radius. And that is just a practical thing that anybody can do outside with string and chalk. And to prove that point, here's a video that I found on YouTube. I sped up a little bit, but literally you just need to fix your string to something that will stay put, and then you go around and you'll draw a pretty good circle. And he'll draw 3 circles just to sort of make this point. And the idea that also between any 2 points you can draw a straight line, that's very practical. You can do that with a string. People will do that on construction sites and have been doing it for hundreds of years. On the other hand, it's not that practical. So for one, any radius, right? I can't really draw any radius. There's some things that would force me well beyond what I'm ever going to travel in a day's time. I can't build string that long. So there's some limits to sort of where it applies. And okay, this 5th axiom is just a problem for, it always has been. This is the parallel postulate here. I want to just pause to kind of remind ourselves what a parallel pair of lines is, and then talk about how those don't exist on Earth, right? So the axiom says that if you have a straight line falling across 2 other straight lines, whose internal angles on the same side, and I'm just going to ignore this less than, let's say, are equal to 2 right angles, right? So you have a straight line, you have a perpendicular, and you have another line perpendicular to that one. Then the 2 straight lines being produced to infinity will always remain perpendicular to a mutual line, right? So that's just okay, there's a big leap going on there. And you might ask, okay, there's 2 ways to hear that. One is very practical. I, as a mathematician, don't want to worry about what happens really far away from me, so I will pretend it away. That's a practical use of mathematics. But you could ask, how does that work for lines on Earth? And one thing that we start seeing in the modern period as people are trying to operate on larger and larger scales is that our world is not Euclidean. So by Euclid's definition, longitudes are parallel. Longitudes are always perpendicular to the equator, which is a straight line between 2 points. It's the shortest distance. But those parallels will always meet at the poles, right? So the Earth is not Euclidean, doesn't obey Euclid's axioms. And that creates practical problems, say for map making, where if we want to make a flat map of our round Earth, we can't do it provably with mathematics without distorting something. So this is Mercator's projection. You see it preserves angles, that's good, but it really distorts things at the poles. And it's not that Mercator made some bad choices. Because Euclid's axioms don't apply on Earth, there's no other way. Space is non-Euclidean. Again, this is an image from the James Webb Space Telescope. And one of the things you see here, so light travels on straight lines in every sense of straight. And you can define parallel lines here. And one consequence of Euclid's definition is that the lines can't approach or diverge from each other. They need to stay the same distance. But here, right there, we see that the lines coming from this galaxy have gotten distorted. This elongation tells you that as the light has traveled to us from that galaxy, the straight lines it travels on have bent in some strange way. So the universe is non-Euclidean. And if we go and say, well, what mathematics allows us to understand what we're seeing? Just like the classics wanted to use mathematics in Ptolemy's system, we need different mathematics to account for that. And here's another image that really powerfully shows, this is an image of the black hole taken from the Event Horizon Telescope a few years ago. straight lines don't come out of that, right? Light travels on straight lines. They all converge inward. That is, there's no parallels anywhere near a black hole, is I think what I want to say here. Okay, so what can we do, right? How can we build a geometry that allows us to make sense of the pictures we're seeing from the cosmos today, that allows us to make maps or navigate on Earth, that answers the various practical needs that people have encountered? And and another way of saying this is like, what does modern geometry require of us? Both practically, but I also am going to push into the imaginative. You know, we need to be able to imagine new ways of doing geometry that will allow us to perhaps make contact with these new data and these new problems that are arising. Okay, so the historical story of this, and this is one of the things that I kind of love about it, is really a story of back to basics. So geometry comes out of questions of surveying, both for the ancients and the sort of pivot to modern geometry. You can really date in the early 19th century, Lobachevsky and especially Gauss. And one of the many things, Gauss is this incredible polymath. He's an astronomer, he's a mathematician across every field of mathematics. He's also a surveyor. He was tasked by, I think, whichever German principality he was under. He was in Göttingen, but I'm going to blank on the geography. Wanted a land surveying and hired Gauss to do it. And so Gauss was trying to measure triangles precisely on a scale of like 100 miles, and he invented new instruments for it. So this is one surveying instrument called a heliotrope. He built a second version of it called a vice heliotrope. And in his investigations of surveying and trying to understand how the curvature of the Earth forced him away from Euclidean geometry, he began thinking and laying the foundations for what are modern geometry today. And if I had to sort of tell you who are the sort of two pivotal figures, and this, Gauss is one, and then Riemann was Gauss's student, and the optional reading that I shared ahead of time, and that I'll talk about in this talk today, was Riemann's habilitation. So in Germany, in the 19th century, and still a little bit today, you had to submit a second PhD thesis to really become a professor. And Riemann submitted a good one, and it's one of the enduring texts of the mathematical tradition, and I expect it to be for as long as people are doing geometry. And Riemann sort of, a way of understanding what Riemann was doing in responding to the challenges to the Euclidean paradigm that had come up from Gauss and others' investigations, is he wanted to build a geometry that was going to be sufficiently general that whatever we encountered in the universe would be addressable by it. And starting, okay, what is that activity? What do we need? Well, we don't want to be able to measure, right? Geometry at the end of the day is about measurement, and we want to measure a bunch of things, but we really want to measure like distances and angles and surface area and volume. Those are the sort of fundamentals. And Riemann noticed that before we can even talk about measuring things that are extended in distance or that have area, we need to think about what we mean by what is an extended thing. What does it mean to be extended in one direction, or two directions, or three directions, or potentially more than that? So he sort of is the first I'm aware of to explicitly put his finger on, and he's conscious of this, what does it mean for something to be extended some finite number of times? We want our theory to be useful, right? This is not just an act of imagination or speculation, but we want it to be able to solve and increase our ability to solve problems that are showing up in activities that humans are committed to, even if they aren't necessarily committed to mathematics. And we want to have minimal assumptions, right? Euclid is something that was serving well for a while, but we pushed past the sort of domain of applicability of its assumptions. And so we want to narrow the assumptions that we have to have a more general and more applicable theory. And then the last thing, this is like the 19th century, we want to be able to use all of our numerical tools. Right? So if we're making measurements, we have quantity, we have numbers, we should be able to use all of our numerical tools, and especially calculus. Calculus is sort of the numerical tool par excellence at the time, and Riemann said we should be able to use that in our geometry. But this is sort of, about it. And he writes his habilitation. One of the lovely bits of math history is this is a contemporary translation by one of the leading English mathematicians of the day. Showed up in volume 8 of Nature, so just a bunch of things going on here. And he calls this On the Hypotheses Which Lie at the Basis of Geometry. And I can't do better than actually just read from the introduction that Riemann lays down to talk about kind of what sort of project we are in. And in some sense, you can go back to the penguins video, and as I'm reading this, ask, okay, what are the fish, right? What is the tasks that Riemann is setting for himself? And then what I'll sort of zoom ahead and be like, okay, what kind of things have we gotten from this 150 years later? And Riemann, interestingly, anticipates a bunch of these. So I'll just read you from the intro. He begins, it's known that geometry assumes as things given both the notion of space and the first principles of constructions in space. And this should sound familiar to every student who has wrestled with Euclid here. She gives definitions of them which are merely nominal, while the true determinations appear in the form of axioms. The relation of these assumptions remains consequently in darkness. We neither perceive whether and how far their connection is necessary, nor a priori whether it is possible. Right? You can lay down a bunch of axioms that are subtly contradictory, and it will take some people some time to figure it out. Riemann continues, from Euclid to Legendre, to name the most famous of modern reforming geometers, Legendre being in the 1700s, this darkness was cleared up neither by mathematicians nor by such philosophers as concern themselves with it. The reason of this is doubtless that the general notion of multiply extended magnitudes, in which space magnitudes are included, remained entirely unworked. So Riemann is quite conscious that no one had bothered to ask, what are the things that we're trying to measure when we do geometry or we do measurements of space? Maybe we need to attend to those. And he says, I have in the first place, therefore, set myself the task of constructing the notion of a multiply extended magnitude out of general notions of magnitude. And he does this in a very neat way. He says, first, okay, we sort of know what it means to have an extension in one direction, in one dimension. You can go either forward or backwards. So he sort of says, okay, we know what a one-dimensional extended object is. And then we can imagine a sort of one-dimensional variation of a path, where it sort of wiggles along something and maybe makes a two-dimensional object. And it's that kind of that motion sense of extension he sort of builds. And he sort of shows how to go back down. So he really tries to work up in a pretty concrete way for mathematicians. And he will say, it will follow from this that a multiply extended magnitude is capable of different measure relations. So it's stretchy, is what you might hear it as, right? We're not going to pin down exactly what the dimensions are or the internal positions. We're going to imagine that maybe it's made out of rubber or some stretchy, elastic cloth or something. It can have a bunch of different measure relations on it. And consequently of this, space, the actual space that we live in, is only a particular case of a triply extended magnitude. So if we're going to build this theory, we'll probably expect to find some things that are not the space that we live in, but we don't know all the properties of space that we live in, so that's a feature, not a bug. And it says, but hence flows as a necessary consequence that the propositions of geometry cannot be derived from general notions of magnitude, but that the properties which distinguish space from other conceivable triply extended magnitudes are only to be deduced from experience. Thus arises the problem to discover the simplest matters of fact from which the measure relations of space may be determined, a problem from which the nature of the case is not completely determinate, since there may be several systems of matters of fact which suffice to determine the measure relations of space, the most important system for our present purpose being that which Euclid has laid down as the foundation. So again, he's saying there might be different ways to get at this, but let's try to find the one that is sort of the most economical, the most broadly applicable, that makes the fewest assumptions, and that will be the most useful, and we'll sort of proceed from there. And he says these matters of fact are, like all matters of fact, not necessary, but only of empirical certainty. They are hypotheses. We may therefore investigate their probability, which within the limits of observation is of course very great, and inquire about the justice of their extension beyond the limits of observation on the side both of the infinitely great and of the infinitely small. And so he's sort of seeing, okay, Euclidean geometry starts to break down in our application of it to the world if we operate at global scales or if we start pushing really out into cosmological observations. Maybe this will happen with his geometry too, and he flags that as an explicit question. And, there we are. So I love that, and in some ways you can see, and it's historically accurate, there's a direct line from Riemann to Einstein. General relativity is built on the mathematics that Riemann investigates here, and again, this question of does general relativity, does this mathematics work for the infinitely great, the scale of the universe? And that's a source of very active science right now, and the answer seems to be to the best of our ability to measure it. And then he also anticipates, well, it's really hard to measure on smaller and smaller scales. And we seem to think that on the small scales we can measure, geometry behaves in standard Euclidean ways, and he even goes so far as to assume the Pythagorean theorem holds at small scales. But he's sort of agnostic about whether it holds at large scales. And we now have quantum mechanics, and quantum mechanics, to the best of our understanding, tells us that geometry doesn't actually even make sense at small scales. So Riemann sort of anticipates that, and that's still an enduring question that people are trying to figure out right now, right? We have one theory for the infinitely great, that's general relativity, or the Riemann's geometry. We have something else going on at the sort of smallest possible scales. We don't know how to make them match up. This is a subject of ongoing research. All right, and then, so I gave you the intro, gave you kind of a sense of what it's about. How does he accomplish this? And again, this is essentially a synopsis at the end of the thing. And the thing that you see right here is he says, well, let's start by defining what it means for something to be extended, and we want to talk about it being extended once, that's sort of in a line or a curve, or twice, or 3 times, or maybe, because we're mathematicians, we want to be open and extend it some arbitrary number of times. And then he talks about, okay, what is it needed to make sense? How do you go up a dimension? How do you go down a dimension? How do these relate to each other? How do you quantify or do measurements on them? And he says, okay, now that we have our notion of extension, what are the properties of measuring? Like, how do we measure? And what's really beautiful about his approach is that he essentially assumes that an observer at a specific point in the space can make local measurements essentially with a string. They can measure distances, and maybe they can measure angles, but they can't, there's no claim that they can do that at large scales, right? So he really builds it, this geometry at the small scale in a way that sidesteps some of the issues of Euclid just saying a circle of any radius can be drawn. Parallel lines extended to infinity. Riemann says, okay, let's be agnostic about that and just start from the very small and then see how far we can get. And then having built out this theory, he says, okay, let's think about how it applies to the universe or to the space that we inhabit. And he sort of ends with some comments and speculations there. Right? So this is all done in 12 pages. So you see the synopsis coming on page 13 here. And this is continuing to keep my colleagues and my students and myself and mathematicians busy, and I expect it will do for quite some time. Right? So again, in the spirit of St. John's, really encountering the great ideas in the original texts, I would be incredibly sort of pleased and gratified if even one person in the audience was inspired to sort of engage with this. But I think this is a text where it really rewards careful sort of thinking. And I'll then sort of lead us through some of the fruits of that thinking in the remainder of the talk. So you might ask, like, where are the fish? Right? What does this give us? What are the fruits of this geometry? And zooming ahead, to the present, we can see a bunch of uses. So first off, we can start to explain or even reproduce the images that our telescopes are showing us. This is a simulation from NASA. This is a background image of just some view of a galaxy, and we see a gravitational lens, something warping space, moving across it, and you see the galaxies behind the lens start to bend and stretch and twist in the ways that we saw in the actual James Webb image, right? So that's a nice thing. We can do geometry better. Another video, and that is, I think, extraordinary. So, Galileo changes astronomy when he invents the telescope, right? And suddenly we can peer into the heavens with optical telescopes, and he sort of opens up a whole new way of seeing the universe. In our lifetime, scientists have built a completely new way of looking at the universe that can see further back in time than, can see to points in the early universe when the universe was still opaque to light. So if you go back before 300,000 years after the Big Bang, the universe is opaque, light can't travel through it, optical astronomy will never get there, but gravitational waves can permeate space, time, right from the Big Bang. And so they built not one, but 2 gravitational wave observatories, contemporary astronomers. And then they were sort of met with the problem of they have a new device, it's going to give them some new data, no one has ever looked at the universe like this. How on earth are they going to interpret their data? How are they going to know what it is they're seeing? And so the solution that people came together with was, let's simulate the 10,000 most likely forms of black hole collision we can possibly imagine. Based on all the other forms of astronomy they've done, they can say, okay, what's the space of most likely black hole collision that our instruments can see? And then let's do simulations of all of them. And then we'll turn on our instruments, we'll get all the data, and the first question we'll ask is, does the data fall within the 10,000 simulations that we've done? Or do we start getting things that we didn't expect and must something have gone wrong? And in a kind of triumph of science and engineering and human ingenuity, they turned on the thing, and every bit of data that they found matched one of the simulations. And in fact, they saw 7 black hole collisions that matched 7 of their simulations. And this is a video of one of the simulations of 2 black holes colliding and the gravitational waves, the ripples in space-time, which you should think of as suddenly something which was 1 meter apart becomes like 1.01 meters apart. But the distance internally in space changes as these waves pass through. And just to comment on this image, it's a simulation of one of the black hole collisions that was actually observed, where it just completely matched the simulation. What we're seeing here is a 2-dimensional slice of the 3-dimensional space, so they just sort of took a kind of cross-section. These 2 black dots here are the black holes, like the circles are the event horizons, and the green here is a representation of a strength of a gravitational wave, right? So in some sense, you just sort of see this like a wavefront, like a peak of a wave. And they also had to slow this video down by like 100-fold because in actual space, this is happening in, I think, like 40 microseconds or something, very, very fast. And so they slowed it down to allow us to understand what we're seeing. But this is data, or simulation that matched data from the LIGO observatory. We see the 2 black holes circling around each other. The green waves are the gravitational waves that start to get emanated. They start to circle closer, the waves get more intense, and what we'll see here is what was observed, where suddenly they merge and you see this big bright peak, that's the sharpest gravitational wave going out, and then space-time settles back down and is quiet, right? So this is a simulation that they did using the physics, the astronomy that was built on Riemann's geometry, that was then matched to data that was seen from the actual heavens. Great. So those are some pretty good uses, but it's nice to also have some uses that are more down to earth. So I think many of us have used this. I can sort of get around my own neighborhood, but when I was driving here from Albuquerque or driving around, I'm like, okay, just turn on Google Maps. And we're just used to the idea that we have a device that will always tell us exactly where we are on a map and how we should get there. And okay, the mapping software that finds your destination, that's a different type of mathematics. But GPS as a technology that can tell you exactly where your position is relies on precisely coordinated timing between multiple satellites to triangulate your position on Earth. And it turns out that the clocks on the satellites move at a different speed than clocks on Earth because of relativistic effects. So GPS is made possible by the physics that's built on Riemannian geometry. So I'm going to claim that for the geometers, maybe unfairly, but Einstein isn't here to argue with me, so tough on him. But that's another sort of use case right there. It's a practical problem of how do we get around. And a third one, this is sort of very present, is math is for fun. It's for play. Humans like play and imagination. And so this is a video of it's a trailer for a computer game that you can download on Steam right now. I'm not actually paid by Hyperbolica, but I really like this video, and I was like, okay, let me show you some games that people are making. People are making games to explore and play with this math. So I'll turn this on here. And I'll say this is a game that's built on 3 of the 3-dimensional geometries that people have discovered and worked with after Riemann. So there's hyperbolic geometry, and notice right now he's having no ability to hit anything with a snowball. It's really hard to hit anything in hyperbolic space with a projectile because it just diverges. So they play with that in the game. Right now we're in the farm. This is spherical geometry. The world bends towards you as you hit on a trampoline. Or in hyperbolic geometry, the world bends away from you. Right? So they built the geometry into the gameplay in fun and interesting ways. Right, they still can't hit anything. I mean, really, the aim is just really terrible in hyperbolic geometry. But we want to play with things. We want to make games. We want to have fun. I think there's this is a really nice example of it, but people are just sort of getting started about how can we use computers to play with these. All right, and so what I want to sort of close my talk with is talk about what are we finding and how are we finding it? What are the things that my colleagues and my students and I are doing? What is modern geometry? And the sort of one answer is that we found not one geometry of 3-dimensional space, but fundamentally 8 of them. And these are images. I have a colleague, Steve Treadle, at University of San Francisco, who, with some other colleagues, is just an absolute whiz at visualization. And I was just corresponding with him frantically for this talk, being like, Steve, can you get me this video? Can you get me this thing? So this is an image of ordinary Euclidean space, and what they've done is they've tiled it, right? So you want to be able to see the space, and so they just said, okay, we can just take cubes, and we'll move them next to each other, and then we'll put the same object in each cube, and you can sort of see how space, in a kind of hall of mirrors effect, goes back, right? So this is ordinary Euclidean space. But we have other versions. This is spherical geometry, and it starts to, objects get larger as they move further away. That's a weird feature of vision in spherical geometry. Or hyperbolic geometry, where objects get really small really fast. And then there are 5 other geometries that we're still kind of exploring. This one is saying, okay, it'll be kind of spherical in 2 dimensions, but Euclidean in 1, so you have this kind of mixed geometries in 3 dimensions. Here it's hyperbolic in 2 dimensions, but Euclidean in this one. And then there are 3 that are just kind of very strange, and mathematicians are still exploring them. And they go by the names of nil and sol and SL2R, and things are weird in them. And I've talked to Steve about making VR of these, and he says, actually, the human visual system currently resists these geometries. In hyperbolic geometry, our eyes will take 2 different images and combine them stereoscopically into one image like we're used to. But here, people put on the headset and it's confusing and the eyes just won't combine them. So, we're still learning how to explore them, right? And here you can see all 8. They made a video that I'm not going to show all just for time reasons, but I'll share links in the slides where they set it to some sort of pleasing music and you can kind of go, and they just put spheres at regular intervals in the space. This is Euclidean space. The spheres are all in nice little rows. They've got colors. They've done a nice job of figuring out how to render this quickly. And you can just sort of fly around in the space. And so this is Euclidean space. And it'll fly around long enough that you can kind of get yourself oriented. And then it will dissolve and it will sort of shift into a different geometry. So I'll take us through 1 or 2 of these geometries just so you can start to see about it. And then I'll say, if you're curious, you can go watch this at home. It's about an 8-minute video, about a minute for each of the geometries that we're studying. Right? This is what mathematics is for, right? Pretty pictures. And even these tilings of Euclidean geometry, that's a really interesting topic, right? Crystals are fundamentally tilings of 3-dimensional space. Okay, but now we have spherical geometry, and those really big balls, those are the ones that are furthest away, right? Because light, as you go to the other end of your spherical 3 space, all converges. So objects that are far away end up looking bigger in a weird way, right? These ones here are the ones that are sort of near you in the visual frame, and these things there are the ones that are absolutely as far away as possible to be in the space. So that's strange. And you can start kind of playing sort of interesting games, like you could really blow out someone's eardrums by shouting at the antipode at them in spherical space, and then all the sound waves would converge on their ears, and it would be like they were like right here, right? Funny things like that. I'll let us get to sort of 1 more geometry here, and then I'll push on. But if you have questions or comments, I'm happy to talk about other features of what we're seeing here. Great. All right, so hyperbolic geometry is this one. And again, you can see there is a lot going on. There are a lot of balls, a lot of spheres in view, because hyperbolic space gets very big very fast, so you can populate it with a lot of things. And interestingly, and I'll talk more about this, when you start doing experiments, you start building these images and letting people explore them, our visual systems are really well tuned for Euclidean and for hyperbolic geometry. For both of those, you can actually kind of orient yourself pretty quickly and pretty naturally. And for the others, we're not. And it's a sort of interesting question of why, certainly we can account for why evolution would have us well tuned for Euclidean, but why is it also we're well tuned not just for Euclidean, but the other ones? Just an observed feature. All right, we'll see if this transitions. Okay, we'll have 1 more, and then, honestly, I could watch this all night, so great, okay. But you see how things start to get really more distorted as we move into the other ones. So, great, and this, again, this is hyperbolic in 2 directions and real on another. All right, and Ron, I should just ask, I should be done at the hour? Okay. Should I just run through? I mean, we've got 4 more geometries after this. This is great. It's Friday night, so. I'm just going to use this as a time to advertise. I think Steve's an absolute genius, and he has a website where he has a lot of visualizations that he's made, and I'm actually hosting him at UC Irvine in a week and a half. I've been corresponding with him about, okay, can we push some of these explorations further? How do these features work? There's a lot of cool stuff to go on here. Right, so in hyperbolic geometry, in the 2 dimensions, in the last one, in the 2 dimensions that was hyperbolic, things bent away. Here, in 2 dimensions, it's spherical, so they really bend towards each other, like on the surface of a ball, but you have this straight line geometry coming from Euclidean. So in one direction, you sort of know what's going on, but you're sort of in some, you're like on the edge of some tunnel kind of thing. The light bends around in those directions. Right? These are all spheres of the same size, but the light travels in different ways. So when you're looking and you're asking, how does light scatter off them? What will I see? They look like they're different size, even though if you went to them and you measured them, they're all spheres of the exact same radius. Right? So our vision has to be adjusted to understand how objects of the same size behave in these different spaces. Okay, now we're going to start to get into some of the weirder ones. Yeah. So, interesting, these last 3 geometries were discovered when people thought really hard about what geometry is, how we've thought about it, and sort of identified that one of the principles that we've taken for granted and that Galileo explicitly articulated is that space should look the same to an observer at any point in it. And when you say, okay, well, what does it mean to match space from one point to the next, you get this very powerful concept called a group, or a group of isometries, sort of same ways of rearranging a geometry that preserve all the measurements. And Felix Klein, a contemporary of Riemann, sort of said Galilean geometry is the study of these global symmetries, and it turns out the other 3 three-dimensional geometries are themselves groups of isometries, right? So somehow they both encode geometries and they are a geometry. This is the second to last, so for those of you who are looking for this to be over, I'll move on. For those of you who wish this was on loop, YouTube is great that way. The links will be shared in the slides. And again, one thing you see here in this also too, there's something really interesting happening in one direction in geometry, right? You could push further and say, actually, we think that space should look the same at any point and in any direction. And that's true in Euclidean geometry, it's true in hyperbolic geometry, but it's not true in these geometries, right? I mean, it wasn't even true in the geometries where 2 directions were spherical or hyperbolic and 1 direction was Euclidean, right? Those had preferred directions. But you could sort of explain that as well. We kind of built them artificially. Here's something we didn't build artificially, and one weird direction is popping out, looking almost like a tunnel here. But if we turn the vision, we see more of this kind of starscape kind of idea, right? And again, these are all spheres of exactly the same diameter, but the light is distorted in similar ways to how we saw it distorted in the James Webb, right? In the James Webb images, those are all galaxies, but some of them are really drawn out and stringy because of the way the light has traveled to us through space. Something similar is going on here. Ignore this blurriness. This is not a feature of the geometry. That's a feature of, there's hard mathematical choices in actually even rendering these. And it turns out that the ordinary functions that you'd use from ordinary calculus are really slow and don't behave well, but a different class of functions that were discovered for a different reason in the 19th century turn out to create a huge speed up, which they haven't yet made publicly available. But there's like math even in building these videos, right? It's not just mathematicians do stuff and then they feed it to an artist or to a computer engineer or whatever. It's like at every stage there's an interaction between how do we understand the geometry, how do we use it to make pleasing images, what are those pleasing images telling us? Great. Okay, so we've seen some great, okay. Yeah. Steve will be happy to hear how the video is received when I see him soon. And one question is begs, we found these other worlds. There's at least 8 of them. It's a major breakthrough theorem about 20 years ago. Sort of Thurston, after doing a lot of exploration in the 80s, he announced that he had strong reason to believe that any 3-dimensional space whatsoever could be decomposed by simple moves into one of these 8 geometries. It's a far-reaching conjecture, and it was proven in like 2002, and again, that's a major kind of accomplishment in the mathematical world. But you might ask, like, okay, how do we explore these? How did Thurston find them? What do mathematicians use for this? And again, this comes down to kind of 2 basic approaches that mathematicians employ. On the one hand, we like do math, right? We have some numbers, some equations, we compute things, we try to solve some answers, we maybe make some guesses about some theorems, we prove them, all the usual kind of business of mathematics. At the same time, like, this is geometry. So we want to actually try to inhabit these spaces, visualize them, do thought experiments, and there's a complex and powerful interplay between these, right? Where the computations suggest thought experiments, which then suggest either further computations or theorems that we hadn't realized might be true, which we can then prove, and then we can do new thought experiments, and then we can sort of feed that back in. And that is a lot of the life of a modern geometer. So in the last part of my talk, I want to lead us through some of these computations and thought experiments in just one of these geometries, in hyperbolic geometry, to talk about how that goes. And you guys have been very patient and attentive through 40 minutes of the talk, so the only math I'm going to need you to hold in mind is the length of a circle, the circumference of a circle, right? So, but those lengths will change depending on our geometries. So concretely, let's start. If I have a circle of radius r in Euclidean geometry, its circumference is 2 pi r. Great. You can do the exact same computation in hyperbolic geometry, and you get this function here, which is called, hyperbolic sine. But just for approximations, this is about pi times e to the r. And the key thing to note here is that if I double the circle, then I double the length. But if I double the circle here, it gets much, much bigger, right? This difference in linear growth versus exponential growth, that's a first place we're saying something is different about our measurements in this other space. And to kind of help us explore this, Thurston powerfully advocated within the mathematical community we should seek to live in the spaces that we study. We shouldn't just study them from a kind of God's eye view or from the abstract, but we should ask, what is it like to actually situate ourselves in them? What kind of things do we see? Here's Thurston situating himself in a knot. You kind of get a sense of what he was about. I'll also just say, at St. John's College, Thurston is not just one of the visionaries in the geometric tradition, in the mathematical tradition. He's also someone who wrote powerfully, with depth and with insight, about what we are doing when we're doing mathematics in ways that are intelligible to everyone in this room. He has this essay called On Proof and Progress in Mathematics, which mathematicians are actively still referring to, and we're like, right now people are trying to build computers, and there's a question of could you build an AI mathematician? And Thurston anticipates many of these questions and says, well, okay, but what is the purpose of human mathematics? What are we doing? It's more than just trying to know is something true or not. We want to understand why, we want to be able to explore it, we want to be able to play with it. So another great text there. And Thurston sort of popularized a thought experiment, which I'll call Thurston's hyperbolic swim, to kind of explore, okay, what do we do with this difference in the length of hyperbolic circles? And so I'm going to lead you through the thought experiment, and then we'll see this kind of interplay of computation to experiment to computation to experiment, or to thought experiment, to sort of this interplay of mathematics and imagination, as this is actively what I and my colleagues are sort of doing, and what I hope some of you will engage in your own experience with mathematics. So, okay, the hyperbolic swim. The basic idea is you and a friend are swimming in a pool. It's a circular pool in hyperbolic geometry, and it's about the size of a standard Olympic pool, maybe a little smaller. I'll say it's a 25-foot radius pool. You swim for a bunch, and then your friend has to go to a meeting. So she swims to the side of the pool, gets out, puts on clothes, and then realizes that they've left their towel on the other side of the pool, and doesn't want to get back in. They're in their street clothes, that would sort of be a pain. But they figure they can just go walk around the edge of the pool, and at all points in that walk, they'll be only 25 feet from you, so they're still with you, they're still chatting. And the question is, how far have they walked by the time they reach their towel on the opposite side of the pool. And again, for Euclidean pool, Euclidean space, the answer would be, okay, 25 pi is about 75 feet. Great. Yeah, I did that right. Any guesses for this hyperbolic pool? What'd you say? Yeah, okay, but what is that, how big is that for those of us who can't exponentiate in our heads? Yeah, I mean, being able to do this for fast estimates, I'll save you the trouble, but it's halfway from Earth to the sun, right? It's pretty far. At a certain point, you're like, I should just take off my clothes and get back, change back into a swimsuit and go across. This is also why it's so hard in the video game to hit people in hyperbolic space with a snowball, because if you're just a little bit off, by the time your snowball has traveled the 20 feet or whatever of distance to them, it has diverged exponentially on its straight line, right? We see this in the swimming pool. And one thing that's sort of rich about this is all we did in this thought experiment was thought about the length of a circle. But we see something surprising, and so we can go deeper. So you might say, well, how do we explore this space further? How do we really live in it? And something that mathematicians do all the time is we observe that the laws of classical physics are actually pretty much agnostic about the background geometry. You can formulate Newtonian mechanics, the idea that an object in uniform motion remains at motion. You can formulate ray optics, acoustics, in all the standard ways, irrespective of the geometry. And so we can start using those, and we can do computations with those rules. And if another way of saying this is like light and sound and water waves, et cetera, travel on the shortest paths. Reflection and scattering are locally just like usual. This is underpinning the video by Steve and his colleagues that I showed you. And our vision and hearing will function, therefore, in the same way. And one thing to notice is that human vision and hearing depend on the area of spheres. The volume of my voice reaching your ears is essentially proportional to the piece of the spherical sound wave emanating from the speaker, right? If it wasn't amplified, it would literally be emanating from my mouth. Okay, there's some interference because of multiple speakers, but to first order, that's true. When we're seeing things, the size of an object in our sort of visual field is proportional to the area of the sphere at that radius that we're seeing the object. So the reason why things far away look small is because it's a bigger sphere that they're a part of. And this is, mathematically we see this in inverse square laws in Euclidean space because spheres' surface area grows at the square of the radius. But we can do this computation, so we started with the length of a circle. Okay, I slightly lied. You have to have the area of a sphere, but bear with me. It's very similar mathematics. So the surface area of a sphere in Euclidean space is 4 pi r squared. In a hyperbolic space, it's pi e to the 2r. Right? So again, you have this now quadratic versus exponential thing. And when you start thinking through the swim, I'll now situate myself there. So I've decided that I'm going to go and swim at the end of the pool, but I'll keep talking with you. And then I swim 6 feet, and I turn, and a hyperbolic sphere of radius 6 feet has the same surface area as a sphere in Euclidean space of radius 300 feet. So I can't even see you. I can barely make out your face at 6 feet away. When I stand out of the pool, I can barely see my toes, right? We have to shout to each other, even if we're like 5 or 6 feet away, because the sound dampens so quickly in hyperbolic space. So hyperbolic space, as you begin to think about it, it's very big, everything looks very small, it's hard to see, it's dark. And that's a different vision than you got from Thurston. And you can sort of run this thought experiment a little further, and you say, okay, we saw in the video game that it's hard to hit, it's hard to throw things, it's hard to play catch with a ball, it's hard to hit something with a projectile. Sound waves dampen very quickly. So one of the good things about hyperbolic space is it's really hard to have a war there because bombs just aren't going to do much because they'll dampen. I think things that on Earth have 300-foot blast radiuses, more than 10 feet away, you're going to feel a little bit of a breeze, right? So that would just tamp down a lot of bad behavior. Maybe at some cost, but things happen. And you can push this thought experiment further, and this is a line of thinking which was, I think, only really asked quite recently. So this is a picture of Reggie Wolfson. This is the choreographer I work with. I've had the great privilege of working with him and his company for about 12 years. And at the beginning, his company brought me into the rehearsal studio because there were formal patterns in some of the movement that they were sourcing from sort of Senegalese and Africanist percussion and dances to this percussion that just didn't make sense. They're trained in the sort of high American postmodern tradition with deep roots to also like other American vernacular dance forms. So they had drawing from a wide array, and drawing from that wide array, the things that they were seeing didn't make any sense. And so Reggie had the idea to say, what if we brought a mathematician in to help us? Maybe there's some other mathematical structure here. And so I spent 5 years working with them, going in and saying, okay, Reggie had reasons to believe that maybe some things they were seeing were fractal. And so I went in and I told the company what a fractal was, and it's sort of mathematicians think about symmetry as repetition under some transformation, and for fractals, it's repetition under dilation, sort of stretching or shrinking, and they sort of talked about what are the ways that might show up in a dance. Reggie, in my first session in the rehearsal studio, gave me 3 dancers and said, make a fractal dance, and I was like, I cannot do that, I've never choreographed anything. But with some support, we were able to get a motion. There's a lot of like, okay, what can math do for dance? And the answer was quite a lot, but as we worked more together, Reggie started observing with some force that mathematicians are very proud. We have a very old tradition where we thought about space and motion and time, but the same applies to dance and the choreographic. This is a tradition that goes back thousands of years. And Reggie started asking, well, where does the choreographic knowledge make contact with the geometric tradition? And this boiled down to a question. I started explaining to him these Thurston thought experiments, and he listened for a little bit, and he's like, wait a second, let me get this straight. When you guys are trying to live in the spaces, what you're doing is doing that as disembodied eyeballs or disembodied point particle observers. What about our bodies, right? We are extended beings. We're not just at a single point. What happens when you do this with our bodies? And if you run that in this swimming pool experiment again, you get some very weird things. So I'll sort of lead you through this thought experiment and then close. But in Euclidean space, if I walk, right, I walk just in a straight line, then my shoulder, every point of my body is traveling in the line perpendicular to the plane of my motion, right? And I walk, and I just comfortably feel the power of the parallel postulate as all the points in my body stay exactly the same distance away from each other, no matter where I am, and I can just walk around. And this is actually so powerful that it is a fundamental principle of classical physics known as Galilean relativity, which predates the relativity that we're so used to from Einstein, but says that if you put me in a dark box, I couldn't tell the difference between the box being in uniform motion and the box being at rest. And we see this about us all the time. We now know that the Earth is orbiting the sun, and the sun is orbiting the center of the Milky Way, but to us, it just feels, because that's uniform motion, like we're at rest on Earth, right? So that is Galilean relativity, and that's fundamentally based on Euclidean space. In hyperbolic space, it's still the case that if I try to walk, the points of my body will travel in straight lines perpendicular to the plane that I'm going. All of that makes sense hyperbolically. Where things go weird is that those lines will start diverging from each other exponentially quickly. So if I start to walk, the same force that you feel in sort of g-forces, when you're accelerating around a turn, you feel that kind of push to get your body to go onto that non-straight line, I'll feel that internally as I walk. My body, the straight lines will start to pull it apart, and if I walk too fast, I could actually like tear myself, right? So I've got to go very slowly because I can feel the curvature of space in my body. And you could do these thought experiments also like in spherical geometry. If I walk too fast, I'll crush myself, right? Because the straight lines will just all run into each other, and that will also be weird, right? So you sort of see some of the questions, you're like, wow, okay, that's very different from how I'm used to thinking geometrically. Where else is my mathematics maybe in need of adjustment? What kind of questions might I ask from that? What kind of theorems might I speculate about? What kind of computations might I want to do? And that interplay of the practical things we want to do. We want to make sense of the pictures in the heavens. We want to be able to get from one place to another and know where we are on a map. But we also want to engage in play. We want to engage in imagination. And there's this interplay between practical and computational and imaginative. That is what drives geometry from Euclid up to the present. So I'll end there, and thank you so much for your attention.